So, hello everyone, and a very warm welcome to the AI4EAC Introduction to Agriculture Challenge webinar. This webinar forms part of the AI4EAC Innovation program, which has been running now for a little over 5 months. This is a program, for those of you who aren't aware, this is a program of courses, webinars, challenges, and all of this work is leading to a final challenge weekend where participants from all over the East African community can take part in a final hackathon style challenge in at various levels of difficulty and at focusing on various topics. There are 4 challenges taking place on that weekend, which will be next weekend, the 28th and 29th of March. The challenges are focusing on health, finance, education, and agriculture, with agriculture being the most advanced challenge on the weekend, and that's what we're here to talk about today. I should introduce myself. My name is Paul Kennedy from Zindi, and I'm really pleased to be here with colleagues and partners from the CGIAR. Mostly we're going to be hearing from them as well as from my colleague Azer Ksouri from Zindi, and our colleagues and partners are going to tell us all about the challenge design, the research that helped to generate data set behind the challenge, some of the reasons why this is a relevant and important challenge. And towards the end, you'll be able to hear a little bit more about the specifics of the challenge, what the challenge entails, how you can participate, and even get some hints about how the challenge will be evaluated so that you can prepare appropriately. So I don't want to speak for too long. Most of the time will be handed over to our partners, but I do want to take you briefly through some information about the AF4EAC program for those that aren't aware. As mentioned, there are 4 streams. Those streams involve webinars, courses, and challenges. Today, we're focusing on the agriculture stream. In terms of the challenge weekend that's coming up, as I said, it will take place next week. In fact, next weekend on the Saturday and Sunday, 28th and 29th of March. The challenges are attracting more than 3,000 students from around the 8 countries of the East African community. And it's we are counting at the moment as many as 100 universities participating. It'll be a chance to put newly learned skills to the test with live challenges on the Zindi platform. And this is a hybrid event, so you can participate entirely online on Zindi. There'll be a live streamed opening ceremony on Saturday morning, but there are also universities around the EAC that are serving as hosts. So if you're in a major city like Nairobi or Kigali, there are university hosts where you can go and participate and feel the excitement of a hackathon live. We're overall across the 4 challenges giving away more than 30,000 US dollars in prizes. And that also includes swag, it includes internships and other opportunities for winners and people who do well in this competition. For more information, you can go and look at zindi.africa/AI4EAC. I will also share some of these links and information in the chat. But for now, I'd like to hand over to Ellena Girma from CGIAR to take us into the meat of the program today. Ellena, over to you.
Thank you, Paul. I hope y'all can see my screen.
Yeah, we can see it. Thanks. You can go ahead.
Cool. So my name is Ellena Girma. I'm here with the Alliance team from the CGIAR. We work on various computer vision and natural language processing tools within the agricultural space. And we'll be taking you through what a little bit of the work that we do, and then also how you guys can get involved with the challenge. Alrighty, so what is the current state of agriculture at the moment, right? We know that 20% of the world's cropland is showing reduced productivity due to human degradation. And this is actually worsened by climate change. And when it's worsened by climate change, that goes back to feed into this loop of worsening productivity. Additionally, we know that 70% more food is needed by 2050 to feed the growing population of the world. And each 1 degree Celsius in temperature increase of the Earth as is will result in at least a 5% reduce in crop productivity. And all of this kind of makes agriculture a very, very crazy space to work in, specifically because agriculture is a source of income and livelihood for so many people, especially in the global south. And for food, for livelihood, education, and upward mobility, it's a very, very key space for improvement to happen in. And this improvement can be supercharged, as some people say, by AI. And we're trying to figure out what's the right way and useful way to do that for our different stakeholders, primarily our smallholder farmers. So again, like this, the climate change is also increasing at a very, very fast pace. It explains about a third of global crop yield variability. Right now, it's estimated to about like 20 million tons of productivity lost every year in just the major crops. And we know that it impacts differently across different crops. For example, earlier I spoke about a 1 degree Celsius in warming can cause 5% crop productivity loss. But actually, for something like wheat, for example, a 1 degree Celsius temperature increase above a threshold of 2.38% can actually yield in like more than 8% productivity loss. So this just kind of keeps compounding and getting worse. And us as the CGIAR or the alliance, a team within the alliance under CGIAR, which is a research consortium working on creating a food secure future, a climate resilient future, we have different areas of work. And our team is trying to figure out which areas of work AI might be most impactful for. And our areas of work are plant breeding. So breeders out there who are trying to look at the varieties, the different crops that are available, what types within each crop, for example, in beans, what varieties are better performing in different areas, and trying to improve them based on farmer needs. We have gene banks to ensure that all the different diversity in these varieties is well stored and documented. We have work streams in adoption. So if the seeds are created, it's really important we have very clear avenues to get those seeds to the farmers that can best benefit from that variety. We have work in policy, so our typical science-based recommendations, whether it's to NGOs, other actors, or governmental teams. We have work in landscape and also sustainable farming. And our team specifically, we're focused on these two areas of work of plant breeding and adoption. So ensuring that we have the right data to determine what seed is best for what population and thus then getting the right seed to that farmer. So what is the current space of plant breeding? So right now, we are really focused on this issue of phenotyping. Phenotyping is characterization of a crop. So visually looking at a given plant or a variety and assessing how it grows, how it handles stress, how much it yields. And much of this work is actually being done in the global south, especially with pen and paper. So this can bring a lot of error. It's incredibly hard work. It requires very high skill to ensure that you're consistent across the different locations that you're testing at, but it's very prone to error, right? That's the first thing. Second thing is right now the speed of phenotyping and then releasing a new variety can actually take 10 years. And after this 10 years has passed, where a new variety has been released, the climate has already changed, right? Climate is changing over seasons at this point and not decades. So that new variety no longer has the environment for that variety to succeed is no longer there. So let's talk about this a little bit more. So we have phenotyping, it's being done with pen and paper. We know it can be error prone. We know it takes quite a long time to develop a new variety. But even when testing is actually working well, they can only go to a few sites because people are limited, right? When we have highly skilled technicians that have to go to collect this kind of phenotypic data, you can't send them everywhere. And everywhere is important because that's where the farmers are. If you can only send them very close to your breeding station, you're not really testing for the environment and management condition that your farmers are actively living in. And then when it comes to integrating technology into these kind of breeding teams, typically we kind of like, over engineer our solutions, right? We go to drones, we go to like really highly specialized tractors that can scan an entire field in a very short time, but that's not accessible. They're often too costly. They're not available with the right skill set in that environment that they're being deployed in, or fragile. They're not ruggedized enough to work in the environments that exist in the global south. So we were kind of thinking, what's there and available within the global south that can allow the integration of technology, but in a way that actually supports the different users. So right here is when we're trying to bridge that gap, and we've developed a tool set of smartphones that are relatively ubiquitous around the global south, and a push cart, like a bunch of metal kind of welded together with very simple structure of tires, metal bars, a place to mount your phones, and handlebars so you can drive, and an umbrella to keep you, safe from the sun. And we've developed a bunch of image capture protocols to enable standardized image capture in a very short amount of time, so ensuring efficiency in this state. And then if you take away that whole component of the push cart and just stay with those phones can now go anywhere. If we have a lot of youth that are coming into the work environment or the working ages that don't necessarily have opportunities to utilize their skill set that they got through university, and they're educated, they have their phones, and they're ready to work. So now anybody can go to any farm really and take the kind of data that we need to better characterize the crops in those areas and get the right data to the breeders for better decision making. So yeah, this we've scaled across Tanzania, and we're now having a lot of activity in Uganda over the last year especially, and we hope to just can kind of keep going from there. Now let's zero into the specific conversation we want to have about phenotyping. And we're going to be focusing on common beans and specifically flower detection. So flowering is a period of 2 to 4 weeks where flower buds appear and they turn into open flowers. And then those flowers can dry up and convert, and as the petals fall off, they convert into pods. So this is a really important time for the growth cycle of beans. And it requires a daily observation to determine how long it took from planting to when a specific stage has been reached for a given plot. So I've put some examples of how flowers can look. So think already like we're looking at multiple classes within this flower problem, as well as plants. So a little bit more on why are flowers so important? First of all, it marks an important transition from vegetative stage to a reproductive stage. And that means now the plant is taking all the energy was using to develop the leaves and kind of get bigger and more vigorous to developing the reproductive system of the plant. So this is what actually is able to help us understand yields early on. And then second is flowers are an important signal for our breeders for how well that variety is going to do under different stressful conditions, whether it's presence of disease, drought, or like different kind of water stress or nutrient stress. The flowering state tells you very quickly how well that variety is going to do, because if it's experiencing stress and that given variety is not resistant to that kind of stress, the flowers are actually going to abort, because the plant is going to say, okay, I have a limited amount of energy and I'm going to conserve it or utilize it among a smaller group of my reproductive organs. And then next is, it's a very important indicator for maturity class. So we have early flowering and then late flowering. That just means how long it took for that given variety to reach the stage that breeders are interested in. And something like early is very useful to recommend for short, unreliable rainfall, and we know that it matures early, so it should be fine under short rain. Whereas late is, the opposite. If you know that a given area has reliable climatic conditions and it gets longer rainfall, it's probably better to recommend the later varieties for them. And finally, and very, very important, it's an early predictor of yield. So our flowers convert into pods, and then those pods are the ones that hold all the seeds that are then harvested. With the pods that are harvested, and then you shell it out to get the seeds. That's what yield essentially is. So it's an early predictor for yield. So now taking us to what the challenge here is and what we're trying to do at this space, and how we'll utilize the outputs that come from here. So the problem, right, is that breeders need to be able to know how many days it took for a given plot to have 50% of the plants with at least one open flower. Right, so we're going to give you images of common bean plants during the flowering stage, and we're going to request that you use computer vision to locate these open flowers, closed flowers, and the plants. It's really important to think about the plant concept for our downstream use, because we have to be able to associate a given flower to the plant to properly say these number of plants have at least one open flower, right? So the task is just, we're focusing on segmentation at this point. And I hope you can see the animation on the right. It's just showing how we think about the different classes, the ones in red being the closed buds, the ones in green being the plant itself, and so on. So we develop, we take those annotations, we develop a model that can successfully detect these plants across our images for a given plot. And it's supposed to look something like this, the output, right? This is just to show our push cart would typically drive in between like rows of plants and thus image on each side, and then you'd get the output. And finally, we'd be able to deliver the use case to our breeders of how long it took from planting to when the threshold of 50% has been at least reached or just slightly passed. And this gives us quite a strong quantitative assessment of flower stages during the flowering development. I hope you can see the graph, and the x-axis is the date, and then the y is the percent of plants with at least one open flower. We're trying to get to that 50% threshold, and the line in blue shows how that value is reached during the different images from each day. So it's time series data that we would like to extract from this, the outputs at the end, and we compare it to what breeders who were observing the exact same plot got, which is the diamond in gray. All right, that's it from me. I want to pass it on to my colleague Brighton, who will be taking us through a lot of the data cleaning and annotation components.
Okay, thank you, Ellena, for the good introduction. And my name is Brighton. I'm working with Artemis as a data quality analyst. So we know that before any AI model is trained or before any result are produced, everything depends on the quality of the data. And in our context, dealing with agriculture data, such as plant images, the way we prepare our data determines how reliable our outcome will be. So from capturing the image from the fields to the annotating them, each step is a crucial in contributing to the quality of the data. So I'll take you through our data preparation pipelines, starting with data collection through to annotation, where I'll spend some time explaining how the process was. So from the data collection, we have been collecting thousands of images across different protocols and across different growth stages, where we are having them at the end. And here determines what next in your preparation process. And this is duration, where after having all thousands images collected from the field, we are doing the filtering, where we are filtering all low quality images. We are filtering all images with blurriness. We're filtering all duplicates. And as well as we categorize, means we select the relevant images to our cases, as the images are in different growth stages, such as vegetative or flowering or podding stage. So in our case, we selected the relevant images in which are flowers. And after then, we organize them to have a clean data set. And after having the clean data set, we go through the annotation process. Next, please, Ellena. So given the type of data that we are dealing with agricultural data that are images collected and in the real field condition with a number of issues, such as a lot of overlapping in them. We have a lot of background noise. So determine what type of annotation that will go with is a plus for training our model and to make them reliable. So given that, we chose to go with the instant segmentation, where it gave us advantage in segmenting each object of interest, being it plant, being it flower open or closed, giving each one mask. Also following the true shape of the object of interest, also separating those objects or those flowers or plants with overlapping cases, as well as avoiding those background noises. Next, please. So after that, we chose the classes that we will be going, and that, as I said, is plant being the flower open and the flower closed. And we ensured diversity across all the classes that we chose, where in plant bin we had plants with single plant stand, as well as multiple plant stands, where we have more than one plant in a single image. And in closed flowers, we had colored closed flowers as well as green flowers. And in open flowers, we had those white flowers as well as those colored flowers. Next, please, Ellena. Next again. So all that were being done to make sure we are having the data that has all labels that we wanted. And through that, we had a way that we could control the quality of it and assure the quality of it at the end. So first of all, we had a annotation guideline where we had clear rules on how to annotate or to know this is a flower close or this is a flower open. As after annotation, we were doing reviewer validation, where reviewer will go through the whole dataset to determine any error, be it missing flower or incorrect labels or any inclusion of the background noise. After then, we were doing just random quality checks, where a subset of the dataset will be checked to ensure the consistency across our data, as well as we were doing the boundary verification, making sure that each mask follows the clear boundaries of the object of interest. So through that, the common issue that you are been checking, as I said, is missing flowers, incorrect labels, incomplete segmentation, and inclusion of leaves or background noises. Next, please. And all of this were done in this great platform, the RoboFlow, where it gave us the room to do things such as good dataset management. RoboFlow also give us the segmentation tool that enables our work good. Also, RoboFlow give us the room to visualize our data set, like in our data, how many flowers are there, being it open flowers or closed flowers or plant bin. So we had the RoboFlow gave us the chance to visualize that so as we can balance the classes for model training, as well as it gave us the room to export our data to do the model training outside the platform. And after then, our data looked like this, where we had 1,309 images, and they were distributed in three classes, plant being open flowers and closed flowers, as it is been seen from the graph, where we had 3,086 plant beans. We had open flowers 6,813, and we had closed flowers in number counting to 8,822. So these were our data that we concluded from RoboFlow and ready for the model training and other post-processing steps that will be following. Thank you, and I can hand it to my next speaker, Juliana.
We can't hear you, Juliana.
Yeah. No, we can't hear you. It was
Sorry, I
working before.
forgot to put the
There we go.
microphone on. Yeah, thank you.
Go ahead.
Okay, so I was saying that now we want to go through some few statistics. So basically the data about also the approaches and the model performances. So in terms of data, we have about 1,400 human annotated images, which cover in total 5 classes, but these include the classes of interest that are plant-based, flower open, and flower closed. The best performance that we have obtained so far in terms of plant-based and for the MAP at 50 is 83.5%. For flower open is 66.1%. So it's important to signal here that this performance were obtained on data splits that will be different from the one that is going to be used for the challenge. For the flower closed, known performance is indicated here because what we have currently is kind of obsolete. At some point, we decided to only focus on these two classes since these are the ones that the breeders use the most. But for this competition, we decided to add the flower closed because it can actually signal earlier, maybe the 50% flowering date. So it's a class that has been added because it's important and can actually help us estimate earlier the trait of interest that the breeder use. The model that we use, the one that stood out, is basically the YOLO family model, notably the YOLO V11 and YOLO V26 that was released quite recently in January. Other things that we tried that help include increasing the input resolution beyond the size of the recommended sizes for Euro model. And this works especially for the flower classes because these are like small scale objects. Another thing that we tried that led to performance boost include SAHI, which consists of splitting into smaller tiles the initial or the normal input resolution, input image, and then use a specialized model, which is a model trained on tiles image in order to make prediction, and then combine all the prediction and take the most relevant after applying NMS, non-maximum suppression. But this strategy is actually the one that gave the 66.1% for the flower open class. But in terms of inference, it took longer than using the original image at once. And the performance gain was not like really much compared to using the whole image at once. Lastly, what we use that work well is ensemble technique. Other things that we tried include using RFTTR, that is a transformer-based model, but it didn't lead to a significant performance boost. And we also use semi-supervised learning approach. So basically, we had a teacher model, then we predicted pseudo-label and used this one for a student model. But that setup also didn't work that well compared at least to what we have talked about in the best model and approaches category. Next slide, please. So for the competition, what is expected is prediction for the instance segmentation task. And the prediction should include the image ID so that we know what image it belongs to, the class label amongst the 3 classes of interest, and a segmentation mask. The submission file will follow the format defined on the Zindi competition page. And for the leaderboard, the metric that we are going for is the mean average precision at 50. Azer will provide more information about that in a few minutes. Next slide, please. So other things that we tried, but in terms of data augmentation, include brightness, blurriness, saturation, rotation, and cropping. So these are the approaches that we use that provided some kind of boost in performance. So we encourage you for this competition to try this one, but also perhaps other approaches. And a way to help to define what could work would be to take a look at the data and see what might be missing. For example, some sample might not be that lightened. That's where you need brightness, and you can see other issue and try to see what type of augmentation could help boost the performance. Next slide. Okay, so here we have a few approaches that we encourage you to try during the competition, but keep in mind that these are optional. So you can categorize them into twofold. The first one being the one that we have tried and that we just talked about, and the second one, techniques that seems promising and that we have not tried yet. So these include multi-head models. So for example, you can have model with one head per class type, multi-scale pyramidal models, and these are specifically good for small-scale objects. Also, you can try things like mixed resolution during training. For example, have resolution or image at 640, 1024, and perhaps even higher. And lastly, one thing that we recommend is to use test time augmentation during inference time. This has shown or has proved to be efficient for other challenge, not necessarily the plant phenotyping based one, but yeah, this is a strategy that can work well as well. Next slide. Okay, so for the platform for training and performing inference, we have 3 types. The first one being the free and easy access one, basically things like Google Colab, Kaggle, and RoboFlow. We also have the paid tools, including AWS, GCP, Azure, and other things that you can try for those of you who has machine with GPUs like gaming laptop. You can also use those one. And one sub setup recommended here would be a mixed one. So you can start, for example, with local machine or a free access tool, and then upgrade based on what you get as result, and go for the paid subscription. Next slide, please. So I want here to emphasize the importance and the potential impact of the challenge. So it's an opportunity to have a lasting impact on future agricultural AI tools for breeders. Notably, this can help reduce manual field scoring, improve the breeding efficiency, and enable scalable crop phenotyping. So I'm now going to hand over to Azer so that he takes you through the rest of the presentation. And then after that, we'll have some Q&A session.
Yeah, thanks, Juliana. Let me share my screen. So, do you see my screen?
So we can see it.
Yes,
Okay,
you can
great.
see.
So, hello all. I will discuss more in details about the challenge design and the dataset overview and some details about the challenge and how to prepare for it. This challenge, you will be asked to build a computer vision solution that detects the plants and open flowers. The data will be tabular, of course, the ground truth and all, and images. For this challenge, we will not have one metric. We will have, Zindi introduced it a few months ago, a multi-metric evaluation. So your submission will be evaluated on two metrics, the F1 at 50 and the mean average precision at 50. And we will discuss this in the next few slides. When you will submit on the Zindi platform, your submission format will require 6 columns. I have mistyped here. You'll need to, there is ID column, and you'll need to submit the class, the score, the X mean, Y mean, X max, Y max for your bounding box detection. Okay, so for the data set, what presented by the CGIAR team, so they presented what they have as data, but there was some processing from our side in Zindi to prepare better the data for the competition. So we have around 1,000 images for train and around 400 images for test. And in this challenge, your task will be to detect two objects: the plant bean and the open flowers. An example for the plant can be this one in this bounded box, and the open flowers will be those small objects. And the class distribution, what you expect to have in this training data is in those around 1,000 images, you will have around 2,000 plant bean and 3,800 open flowers. Okay, now we will discuss a bit the metrics, how your submission will be evaluated. So the first metric, and it will be with a higher weight, it is the F1 at 50. Actually, the F1 at 50 will measure how good the quality of your detection is. How it works, we will look over the ground truth, we'll over class by class first of all, and then we will look over the ground truth. We will look over the predictions. Then, if a prediction matches ground truth, we will remove this ground truth. So any prediction in the future that will match this ground truth will be considered as a false positive. It is an extra detection. So the intersection over union we will use is 0.5. If the intersection between the predicted bounded box and the detected one is over, with some calculation, of course, it is over 50%. So we will consider this as a match. Okay, so as I said, we will look over ground truth, we will look over predictions or detections, and when we are done, if we have an unmatched prediction, it means that the model detects something, but there is no ground truth that matches this detection. It will be counted as false positive. And if we miss the ground truth, it means that there is a ground truth where there is no prediction that matches it. So this will be considered as false negative. Then we will just compute the harmony relation between precision and recall, as usual for F1 score. And finally, we will average the F1 of all classes. So this is the let's call it mean F1 at 50. Okay. So why this metric matters? Because it will reflect the real world performance of the model that we developed with such a threshold, and we will take care about the false alarms or false positives and the misdetection, or what we call as false negatives. And this is crucial, honestly, if because the client is looking for such a solution that will be deployed, on their systems. So having less false positives and less false negatives is crucial for them. And at the same time, we will use the traditional metric for object detection, which is mean average precision. It has a different way of calculation. Mean average precision doesn't penalize too much on if you do over prediction. For example, if this is your ground truth and you predict a lot of bounding boxes, it doesn't care. The essential thing that there is a bounding box that matches the ground truth. So we can say that mean average precision doesn't care about the quality. Really, in reality, it doesn't pay attention to the messiness of your prediction. You for example, for one image for such object, you can predict 1,000 objects and you will get good score. While in F1 at 50, if you predict 1,000 objects for one ground truth, you will get very bad score, because we are penalizing the false positives and false negatives. But the mean average precision will be used in this challenge as evaluation metric with a low weight, honestly, with a low weight, and because we need just to capture, because first of all, it is traditional, and secondly, it helps us to capture the overall model capability, not just on specific threshold. So that's about the metrics. So if you want to prepare for the challenge, how to do it, Zindi launched this AI4EAC Agriculture Practice Challenge, and the task in this challenge will be to develop a computer vision solution that localize and classify diseases present in such cocoa image. The evaluation metric there will be mean average precision. There will be no F1 at 50, and why we encourage you to join this challenge. If you are new to Zindi, so you familiarize yourself with Zindi, how to download the data, how to create a model, how to do submissions, and also you will deal with real life project of object detection problems. So key skills you will develop during this hackathon. So I would say that during this challenge has specificity in object detection, where you have two objects and the scale of those objects are completely different. The plant is so large compared on the image area. Okay, in the image compared to the image, it is taking at least 15% of the image area. But the open flowers are so small; they are not taking even 3 or 4% of the image area. So here, this is a challenge for you, and you will learn how to deal with this large variation in object scales. So the question would be: will you use one single model, or you will design a multi-stage approach for this challenge? And during this challenge, also you'll have the opportunity to try different frameworks, such like ultralytics, or where you will use YOLO models, or MM detection, where you will have access to a bunch of transformer object detection models. And you will have also, again, you will have the opportunity in this challenge to build a multi-stage pipeline. Maybe I will receive a question, but what do we mean by multi-stage pipeline? Simply, like, the simple answer for this is you will detect the plant first, and then as the open flowers are very small objects, the more we give zoomed in images to the model, the more we will be able to have the higher the better will be we will perform the model. So that's what I meant by stage pipeline. That's it from my side. I will look in the chat. If you have any questions, please let me hear from you. Thanks.
Super. Thank you so much, Azer. I'm going to spotlight my own face. Thank you so much, Azer, as well as the CGIAR team. I think it's a really exciting challenge. Really nice to see the real world application and the work that's gone into developing this data set. I think it really adds a lot of richness to the challenge and shows the real world applications, as I said. So as I mentioned, we'd really like to open the floor now to all of you who would like to ask questions. I think the easiest way to ask questions is by typing them in the chat, and we will respond to them as they come up. If you want to, you can also come off mute and ask your question over the microphone, but feel free to ask questions in the chat. So I did see some questions regarding the PowerPoint and the recording. We can make the PowerPoint presentations available. We'll add it as a downloadable file in the challenge itself, so that anyone who needs to look at the PowerPoint slides will be able to do so. But as I say, the recording of the session will be available. We'll make it available on Zindi on the challenge page itself, so you can easily reference what you've heard today. I see a question about whether this is open to everyone around the world. No, unfortunately, this is part of the AI4EAC, that is AI for the East African community. And so the challenge is focused specifically on students that are residing and studying in East African countries. There are 8 countries in the EAC region. They are, make sure I can get all of them. They are Kenya, Tanzania, Somalia, South Sudan, Burundi, Rwanda, Uganda, and the DRC. If you are not in one of those countries, unfortunately, you won't be able to participate in this challenge, but there will be some other challenges available. Always on Zindi, we have a lot of public open challenges. Please feel free to have a look on Zindi and see some other challenges that you can participate in. Yes, so some questions. Hello, I want to know the place where the challenge will be held in and the physical challenge sessions on the weekend. Yes, so we will be announcing in the next day or two the locations of the physical challenge meetups. You can, as I said, you can participate in this challenge entirely virtually, but if you are based in one of the hubs, one of the capitals of the 8 countries I mentioned, there will be physical locations. We will share those on the page. We will also share those in an email to all of you. So you will find out more information about that. As long as you're registered for the challenges, you will find out more information about that shortly. But keep an eye on the page on Zindi, and that'll give you some information. In terms of the physical events, those are really just a way to experience the physical, experience a hackathon in person. There's no need to be present at one of those events to take part. You can take part from wherever you are, but meeting up at a university will allow you to meet other people working on the challenge, perhaps form teams and work together. You can also do that on Zindi using Zindi's platform functionality. You'll be able to connect with other people working on these challenges and experience the buzz and excitement of a physical hack. Okay, I have a question. Okay. Light shine. I see a message. It doesn't really seem like a question for this forum. I want email from Paul Kennedy because I got the issue when I was registered. Okay, so you've left me an email. Okay, I'll send you an email after this and we can try and resolve whatever problem you faced. Sorry about that. Just take note of your email address. I'll send that to you straight away. Okay, this is a question I think for the CGIAR team. How much time could automated flowering detection realistically save compared to manual phenotyping? Ellena, I'll ask if you aren't able to answer that, I'll ask you to identify the right person to do so.
Sure. That's a great question because that's really how we measure impact as well from our end. We've done some back of the envelope calculations as this is a relatively new technology for us in terms of deployment. We haven't had full cycles or at least like one variety completely developed with it yet. But with our back of the envelope calculations, it's up to a 75% reduction in time taken for active data collection. And also, additional information, a little bit that might help. It's not just active data collection that we have to consider, right? So if someone is going to the field to collect that data and it's at the different locations to ensure that they have environmental representation, you have to multiply it by that as well. So it's travel time. So the farther I go out, the longer travel time that I have there. And it's not usually like a day travel for a lot of these collection activities at the faraway sites. You have to go somewhere else for about a week, especially for something like flowering that you have to observe every single day for 2 to 4 weeks. So this cost saving really multiplies in a big way. And our second assessment of cost saving is in the longer term. So even if you can save time of active data collection and travel time within a specific cycle, by being able to add increased accuracy by implementing this method, you're able to save time by avoiding repetition of new trials. It's very common that the breeders don't have the right kind of data that they need to make the selection decision. If I start with 400 varieties that I want to evaluate, and I want to go from 400 to 200, and it's not really clear what the winners are, I have to repeat that again and again at all those locations. So it's a compounding time-saving solution when it can be accurate and deployed correctly, which we're fighting to do.
Super. Thanks for sharing that. Okay, the next question here is again about the physical events. If the university students are on a team, wouldn't they be on a physical challenge team? I'm not totally sure I understand the question. Students are welcome to form teams on Zindi. There is a functionality on the Zindi platform, on any Zindi challenge. There's functionality that allows you to form teams. That's how you would need to create a team. I'm not totally clear if I'm answering that question. Nabil, if I didn't answer the question, please write it out more clearly or word it differently so that I can understand what you're asking. Thanks. Okay, following up, and I think this would go back to you, Ellena. Another question. If we think beyond this challenge, what would be the biggest barrier to scaling the solution across different regions or crops? And is that only applicable to these common beans, or would it be more broadly applicable to other crops? It's a great question.
Great question. Loving these from you. So I'm going to focus on region first for this specific set of flowering. we're trying to make sure that this model is robust and can generalize well across different locations. Right now, we're focused on Tanzania and Uganda, just because that's where we have the most access. We want to continue deploying and getting wider and wider and wider. In our active training set, actually, we have imagery from Colorado in the US and Colombia, just to ensure that we have different expressions of different varieties of like genealogical lines as well within the common bean lines of like Andean and yeah, those lines, to make sure they're well represented in our data sets. So for that, a challenge to scaling is definitely region, making sure we have the appropriate diversity in our data set so it's robust, and we're tackling that quite well, I would say, right now. The second thing of now making it applicable to other legumes, that's a very good one. So it's very trait specific for a given solution. Flowering in another legume like cowpea is like morphologically it's a bit different as well, and where it appears is also different. So we found as we work on different crops, even for the same trait, how we annotate and the kind of classes we focus on and the annotation tasks that we prioritize can be different. So it's a learning curve. And in the long term, as a team, the kind of solution we're trying to work towards is trying to develop an ag FM of sorts that has at least generalized knowledge about different crops, whether it's like a grass crop or a legume or this or that, understanding the plant structures very well so that it can be fine-tuned for very specific applications later on. So it's quite a large chunk of work to ensure that something like this scales, especially if you want it to be effective, which is our goal, right? We want to make sure that this is accurate data we're giving back, because the decisions, they're massive. We're telling farmers what to grow on their land at the very end, and we want to be like very responsible with this kind of tool. But thank you for these questions. They're lovely.
Thanks, Ellena. And I think there's also something to be said with this sort of work, even if the model created, even if the models themselves don't necessarily translate to other crops, there are techniques and lessons and aspects to those solutions that will translate. So there may not be necessarily a direct application, but there's also some indirect applications that's worth mentioning. Yeah. Cool. And then a follow-up from Nabil: how would the university student team participate in the physical challenge? So so Nabil, anybody wanting to participate in these challenges are participating on Zindi. So sorry, one second. They're participating on Zindi. So even if you are taking place physically in the physical challenge, you would join Zindi, but you would just it's just when we talk about the physical challenge, it's you're physically going to a university in order to work. So if you are interested in doing so, as I said, keep an eye on your inbox, keep an eye on the Zindi page. We will be publishing the locations where gatherings are taking place, and you will be welcome to go to those venues. So if you are based in, for example, if you're based in Kigali, I know that Carnegie Mellon University is one of our hosts. We will publish the name of Carnegie Mellon University, and you will be able to attend that venue physically because you're based nearby there. I hope that answers the question. Okay. Oh, and I see a follow-up about in Somalia. I believe Zamzam University of Science and Technology is one of the Somalian universities that it will be featured. But as I said, in all cases, we will be publishing that list, so just keep an eye out. Okay, another question for the CGIAR team, although actually this might be for Azer as well. So question 1, are there augmentation techniques that could unintentionally distort biological features and harm model performance? CGIAR team or Azer, do you have any inputs on that?
Yes, for the first one, I will say yes, even if I can't think right now of any particular augmentation techniques. Since augmentation technique generally modify a bit the image, I will say anything that can modify the shape might likely distort the performance, but that depends because if you, for example, zoom in or increase, that might not affect badly. But if it's some kind of augmentation that will maybe shrink the flower and remove some details, then that could possibly distort the biological features. So I think yes, and that will depend totally on the augmentation technique that is being used.
Yeah, Juliana. I can add something. So it depends on how you will apply the augmentation. So, and on which set. So usually most people, what the mistake that most people do is they will apply the augmentation on both train and test. So they will increase the number of images they have in the data. But when they split between train and validation or train and testing, the validation or testing set will include also augmented images, which will create like leakage like for the model. So the solution here is if you want of course to use augmented to manually to apply what we call offline augmentation, where you augment your training set. You apply it only on your training set, not on the test set, because the goal will be to help the model to be more general. But for this case, for example, for this use case, if one of the augmentation techniques is increasing light or brightness, increase brightness, so it is danger. It is dangerous. So like it has some danger where the risk is that the open flowers are usually white. So if we will apply this augmentation, we may miss or we may visually miss the open flowers. Like the model will not even see it because it will be too white. So we need to be careful when you use augmentation. But if you want to use augmentation techniques for this challenge, I've seen that recently Ultralytics like added a new parameter for YOLO training, where you can use the augmentation package when you can pass like a list of augmentation as a parameter for the YOLO model, which is like great improvement from their side. So just one last thing for this point. You should use a fixed test set or a validation set, and then you use a baseline model with no augmentation. Then you will start trying some augmentation, and you'll see the effect of those augmentation on the fixed validation set. Hopefully, this solution, this answer, like, it was sufficient to. The second question, I think. Okay.
Azer, do you think the second question is better for CGIAR to answer?
Maybe I didn't read it. So.
Okay, so second question here, you mentioned variability in the data set. Okay, so this is specifically around the data set. Have you observed that the models struggle more with specific flowering stages, and how might we address that? So maybe that's for Ellena and team. Any insights
Yes.
into where the models have been struggling up until now?
Yes, sure. So the model struggle with other type of classes that are not included in this challenge. So these are basically the flower dry, the flower fallen, and the flower closed. But from Azer presentation, I think we only focus now on the flower open and plant bin. So
yes,
yeah, these are the stages. I mean, the earlier class that I mentioned are the one that the model struggle with. So flower open is kind of one of the easiest class that the model can handle.
Great. Thank you. Okay, and then another question about the physical event. Is the physical challenge on the 28th and 29th team or individual? You can participate in these challenges in any capacity. You can participate as an individual, or you can form teams of up to 4 people to participate. Okay. I think I don't see any other questions, but we do still have some time. So if anybody would still like to ask something, now's a great time to do so. Please do ask your questions. You've got the experts here. We appreciate the questions. It shows us that you guys are interested and excited about the challenge. Please do ask your questions. Otherwise, if I don't see any more questions in the next 20 or 30 seconds, we can wrap the webinar here.
I'm also going to use this time just to touch back on that question of augmentation techniques. Initially, with a smaller data set, especially, we found that just to touch back on exposure and brightness changes, that really affected false positive rate also of our open flower class, especially because the tips of leaves, they can be overexposed already. And when you change that, it just sometimes caused, again, the false detection of flowers. Open flower class.
Okay, so there's definitely a trap there for in case people want to use increased brightness as an augmentation. That's a good hint. You guys are getting some insider tips here. Okay, so I don't see any other questions. I think then we can bring this webinar to a close. I appreciate everybody's time, especially I'd like to thank our partners at the CGIAR for all their hard work on this challenge and for all their contributions and for making time in their evenings to share some of their knowledge and insights. So Ellena and team, thank you so much. I'd also like to thank Azer for being present to tell us about the challenge. Before we go, I would like to just post these 2 links into the chat for you. Oops, 1 second. 2 links I want to share. If you haven't seen them yet, here are the links to the AI4EAC Innovation Challenge program, as well as a link to the bean flowering detection challenge. So you can go take a look, see a lot of this information that's already available, and prepare yourselves accordingly for next weekend. So with that, thank you so much, everybody. It's been a pleasure. I've been your host, and we will see you next weekend at the challenge. Bye for now.
Yes. Thanks all. See you.